All right, this is worksheet 1 on logistic growth. And so here we go. All right, suppose the population of bears in a national park grows according to logistic differential equation, dp dt equals 5p minus 0.002 p squared. And then where p is the number of bears at any time t in years. And then here's your initial population. Sorry, this is written kind of funny on your worksheet. It looks better. You might want to have yours out and be filling in your homework. You're finding the limit of p of t as t approaches infinity. Actually, it would look like this. The limit of p of t as t approaches infinity. It wouldn't be up in the air like that. Now, remember the good news from our last thing is I don't actually have to integrate this and separate my variables and all of that. As long as I can get it into kp times L minus P, I can do almost, if not maybe the whole problem, if I can get dP dt into kp times L minus P. So I have to get whatever is attached to P squared out of there. So it's 0.0002. Sorry, I was getting out my notes. And sorry, I've lost my notes. Let's go ahead and do it. Okay, so anyway, I've got to factor out 2 over 1,000. So I'm factoring out, let's put this on the other slide and we'll carry it back. 5p minus 0.002 p squared. Did I get too many zeros in there? Yeah, too many zeros. All right, so we have this. Okay. All right, so that I've got to get rid of this for my dp dt to get it into kp times L minus P. And so I'm going to factor out 2 over 1,000, which is 1 over 500. And so I'm going to factor out 1 over 500 p. So I'm taking out this p. All right, now 5 times, let's see, you've got to make sure that you leave behind something that would give you 5. And so if you're dividing out 5 by 1 over 500, you want to multiply 5 times 500 to see what should be right here, or however you think to do it. This is minus p because you took all of this out. 2 over 1,000 is 1 over 500. Before you start, you might want to redistribute and make sure you have 5p minus 0.002 p squared if you multiplied it back together. So I'm going to take this over to our worksheet. So this is 1 over 500p times 2,500 minus p. So you factored. All right, so now I know my limiting factor, no matter what, is 2,500. So the answer to the limit is 2,500. I'm not even reading what my initial population is 2,500. I don't care how many bears you give me. The environment they're in can hold 2,500. All right, so the answer to this, no matter what your population is going to be 2,500. Now, your limiting factor is pretty high, and so now let's do A. Let me change colors so you can see what I'm doing. Okay, so now my initial population of bears that they put in the forest is in the national park is 100, and it can grow up to 2,500. And so we know the solution curve is increasing. Our calculus justification of that is if we put in 100 to our dp dt to our first derivative, it's positive. So, so this is increasing, and it's because dp dt is greater than 0. And we'll go back and sketch the graph of it in just a minute. P of 0 equals 1,500, and the limiting factor is 2,500, so it still has room to increase. And 1,500, 2,500 minus 1,500 would still give me a positive first derivative, so it's increasing. If we put in 3,000 bears into a park that can sustain 2,500 bears, unfortunately some of them are going to have to go away. And so And you can also see 2,500 minus 3,000 is going to be a negative. And so this one's going to be decreasing because your dp dt is less than 0. And then it says how many bears are in the park when the population is growing the fastest. It didn't ask when, but it asked how many bears. Well, if my park can sustain 2,500 bears, then half of that would be 1,250. Remember, half of the limiting factor gives you when the population is growing the fastest. To justify your answer, you could say that's where my second derivative equals 0, and it would change signs if you took time to take that second derivative. It wouldn't actually be hard to take it. You'd have to use the chain rule and changes signs. And we'll just keep on doing these problems, so let's keep going. That was number 1. Oh, we got to draw the curves. I'll do it on a clean slide. All right, so if my limiting factor is 2,500 bears, okay, and you put in 100, then it has time to grow, and it has a point of inflection at 1,250. If you put in 1,500 bear, then it's too high. It'll still grow, but can't grow very much. If you put in 3,000, the population can't sustain that, and some of them will die off, or hopefully just go find somewhere else to live. So those are really all of these are logistic equations, but this is the most common that people study right here. All right, so let's go to 2 and 3. And by the way, if you want to try some of these on your own, you might be ready for that, depending on how much you understand what I'm doing. You might want to watch a couple more, but notice in Worksheet 1 and Worksheet 2, the answers are provided. I would strongly suggest you hang in for number 2 and 3 before you try anything else on your own, though. Okay, so anyway, suppose a population of wolves is growing with this logistic equation. Well, it's not in KP times L minus B form. I got to factor this out. So that's 1 over 100, P comes out, and 3 times 100 is 300 minus P. So this is my dp dt factored out. You could distribute and double check and make sure you got it right before you answer. All right, so this is one of those multiple choice problems off an AP exam. The limit of the population as you approach infinity approaches 300. And I'm not sure I even did that way back here. Hang on, it was important enough for me to talk about. Oh, I guess I did. Yeah, okay. The limiting factor. So let me go back to this. Okay. And so we know that the limiting factor is 300, so that is true. And we know the growth rate is growing the fastest at half the limiting factor, so this one's true. If it's greater than 300 and the limiting factor is 300, there's no way the wolves are increasing. Also, you can see if it's greater than 300, your first derivative would be negative. And so it would just be 1 and 2 only. All right, number 3. Okay. The rate dp dt of the number of people at a dance who have heard a rumor follows this logistic differential equation. You can read a little better on your sheet. Some of my words, I guess, are cut off. Let me see if I can bring this down some. There we go. Is modeled by, I guess that's as good as I can get it, is modeled by the word logistic differential equation. There's 2,000 people at the dance, so that's your limiting factor. Short of social media and cell phones, that's as many people that could hear the rumor. At 9 p.m., the number of people who have heard the rumor is 400, and we know dp dt, it's increasing at a rate of 500 people per hour. This is a rumor to dance, girls, but just think about how fast the virus is growing right now, and the increasing at a rate of 500 people per hour or whatever. All right, so now we're going to write a differential equation. That means a dp dt, we're writing the equation of the derivative. All right, so we're trying to fill it into kp times L minus P, given this information. All right, so I'll erase things as I know them. I know my limiting factor is 2,000. And so now I just have to find K. Now I know the rate of growth is 500. dPdt is 500 at the moment that the population is 400. So I put in 400 for P. And now I can solve for K and fill it back in. So I have 500 equals 400K times 1,600. That gives me 6,400 altogether K. All right, so what I did there was I multiplied 400 times 1,600 and got 6,400. So K is 500 over 6,400. Cancels. And you have 5 over 64, which reduces, I believe. So I don't know really how to work this calculator very well yet because I just got it. 5, what did I have? Oh, 5 over 64 doesn't reduce. So I feel like I've done something wrong. Just a minute. You may can see, oh, I'm sorry, I didn't have near enough zeros. You may have noticed that. Sorry. Okay. This is 400 times 1,600. Write it like this. Okay, so 16 times 4 is 64, so it should have had 4 zeros on it. You may have caught that. So K is 500 over 640,000. Again, people that do this obviously deal with really big numbers. So I could put K as 5 over 6,400 and get it right on the AP exam. But if it's multiple choice, I'd want to know what that number is. So I'm going to go back. Let's see if I can go back to my original window. Let's see. Let me go to graph. Close. I'm trying to get back to the calculator. I'm having trouble getting back to the calculator. Let's see if this does it. Let's see. Usually I'll hit second, quit. Maybe I'm back to the calculator. 5 over, I think it was 50. Now I've already forgotten what it was. Sorry, girls. 5 over 6,400. Okay, so it's 5 over 6,400. Gives me this decimal. And I'm guessing I can do math fraction. And so it's 1 over 1,280. All right, so my formula, sorry that took a while. I didn't want to do all of that work because it's a lot easier than this. So I'm going to go through it a little bit quicker. All right, you want your KP times L minus P. L is your limiting factor, so you have KP times L minus P. And that equals dPdt. And then I had the information that dPdt was growing at a rate of 500 when the population was 400. So I had K times 400 times 1,600. That gave me K was 1 over 1,280. And so the answer to number 3, I'll write up here, is dPdt equals K P times L minus P. And so you wrote your own differential equation from the information. All right, now let's go to number 4. I think you should watch this one too, actually. I think it's up here, number 4. By the way, all these have smiley faces underneath them, but you can't see them. All right, so number 4, here's your population of animals and the word logistic, and we're given dPdt, where T is measured in years. Notice it's already factored into KP times L minus P. All right, so our initial population is 20. I can see my limiting factor is 100, and so right now I'm having to solve for P. I have two choices. I can separate my variables, put the dt over here, put all of this over here, and do partial fractions, or I can use the trick that you're allowed to use for writing the original equation. My limiting factor is 100, that goes on the top, times e to the something, okay, t. And then to get your coefficient, you multiply these together. Get a different color pen so you can see what I'm talking about. You multiply these together. 0.01 times 100 just gives you 1. And then we're going to say L minus P over P, our limiting factor, minus our initial population over the initial population. So it gives me 80 over 20, and so that number goes right here as 4. So I have 100 e to the t over 4 plus e to the t. Some people you'll see, those of you that study this, which could be many different people, you study it in environmental science and obviously in medical analysis, Center for the CDC's, got people looking at this, and new models are coming out all the time. I just saw a logistic curve on the news a little while ago. And so some people also write it like this. They divide the top by e to the t, that's e to the 1t, or e to the t, which gives you 100. And they divide this 4 by e to the t, and that gives you 4e to the negative t. And if they divide this by e to the t, that gives you that 1 that you may remember seeing. So some people write it this way, and some people write it this way. It actually doesn't matter. You get the same thing. I'm going to use this one right here, 100 e to the t over 4 plus e to the t. I just rewrote this one to answer B. So I would go to my calculator, and I'd go to my whiteboard and type in my equation, which is 400, was it 400? 100. 100. And this is just like doing it on your graphing calculator. And on the bottom I had 4 plus e, it's 100 e to the t. And then I had over 4 plus e to the t. So e to the t. All right, so let me move out here and close that parentheses. And now on your calculator, you could actually go to table and fill in whatever value you wanted to. I don't really see a way to do that on this one. So what's the question? Find the population when t is 3 years. On your, you could just go to table and fill in 3. Here I see it's, let's see, it shouldn't be 48,377. The answer ought to be 83.393. So let me go back to my whiteboard. First of all, I want to get rid of this. And 100, oh, I didn't put divided by. Okay. All right, so that makes more sense. I'm sorry, it wasn't matching the answer on the answer sheet. Now I've got something wrong again. Oh, it didn't put my parentheses in. I'm just going to go here, I hope, and insert a parentheses. Okay, sorry. You'll have an easier time. All right, you see right here that if I pull it down to where 3 is, you see 3 matches up with 83.393. The 3 decimal places. So at 3 years, you just go to table 83.393. And this is population of animals, so I guess animals. All right, then use your answer in A to find out when the population is 80. So I would go to my calculator, and I'd want to go to here and see when it actually hits a population of 80. Now let's think about what our window would be this time. Usually my time frame's kind of small, and here my limiting factor is only 100, so I'm going to go up to 100. and then I'm going to graph. And I'll see the logistic curve, and then you'll go to second calc intersect. I'm just going to go to the fancy way to do it here. Let's see. So I'll move it and it locks on. And so I get 2.773 or 2.772, whichever one, truncated around it. I'll call it 2.773. And so this one would happen at 2.733 years. All right, so the key here is that if you're asked this to go back and find the original, you're not expected to integrate, but you got to remember all of this stuff. That is your limiting factor, and then how to get your e exponent by multiplying your k. You're multiplying these two things together to get this number right here, this number. And then this number out here comes from L minus P over P. We'll do a couple more. All right, the last one on worksheet 1. Suppose a population develops according, here's the word logistic. All right, this one's not in KP form. So I'm going to divide out, this is 5 over 10,000. So this is 5 over 10,000. All right, which is 1 over 2,000. All right, so I'm going to factor out 1 over 2,000 P. I can take a P out of both of them. And then to figure out what number goes in here, I take 0.05, which is 5 over 100, times 2,000. Because I divided out 1 over 2,000, so I want to know what's left. All right, so I believe this, what's left is 100. And then you can double check it by distributing. Okay, so dp/dt, this is normally what you'd be doing. The carrying capacity is 100. And the slope, here's a slope field. So review of slope fields, here's a slope field. And the carrying capacity is 100. So that's your horizontal asymptote. Where are the slopes close to 0? I notice the slopes are close to 0 at 0. And they're also close to 0 when they get close to 100. In fact, what that means is when you don't have anything, it's not going to grow. And when the logistic curve starts to get too close to 100, your growth rate starts to level off. So your derivative should tend towards 0. So it happens when you're close to 0 and close to 100. Okay, so I'm going to put in my carrying capacity limiting factor again. All right, so where are they the largest? Where are your slopes the largest? Your slopes are the largest at half your limiting factor. It should look like the slopes are higher right in here. I'm going to erase that so that you can actually see them. But if I draw on one of them, you see that's the steepest that they get right here. Other than that, they're more flat. So they're a little steeper right here at 50. And so that's when your slopes are the largest, at half your limiting factor when the population is 50. And when are the solutions increasing? The solutions are increasing as long as the population is less than 100. Your initial population, I'm sorry. When your initial population is less than 100, anywhere down here underneath here, they'll be able to grow following my slope fields, okay? If they're decreasing, if I put in too many things into this environment, something over 100, if I put in 150, you can follow your slope field and they'll decrease. And so it's all pretty quick based on your limiting factor. Your limiting factor is 100, and it's going the fastest when it's half the limiting factor, which is 50. And as long as you stay under 100, things can grow. If you're over 100, things will decrease. So we entered this. All right, use the slope field to sketch initial solutions for populations of 20. All right, so let's do that one first. So 20, if I try to follow the slope field through here, it goes sort of like this. And then at 60, I follow the slopes and it goes like this. And then at 120, I follow the slopes and they're going down toward my limiting factor. And so that's this part. What do these solutions have in common? They all have the same limiting factor of 100. So they have this part I'd squeeze in here somewhere. They all have a carrying capacity or a limiting factor of 100. They all are going to gravitate toward 100. How do they differ? In a few different ways. Two of them are increasing and one of them is decreasing. They also differ in their concavity. Which solutions have inflection points? Only when your initial population is 20 in this scenario, but anytime, well, the only one with the 20, but as long as they gave us something under 50, we would have a point of inflection. And at what population level do they occur? And so that occurs when P is 50. So your point of inflection occurs when your population hits 50. Let me get a different color pen. When your population gets to 50, you get a point of inflection. And so if you put in something over 50, it never even has a chance for a point of inflection. All right, so that's worksheet 1. If you need to take a break, take a break. Or if you want to try worksheet 2 on your own and then check the answers or the video, that's fine. You just do what you need to do. So now I'm going on to worksheet 2, which also needs to be done. So I think I have it all on here. It's not moving. Okay. So I believe this is worksheet 2. Let me check. Okay. Here we go. So maybe you're just tuning back in. Okay, so, sorry, let me check my phone. All right. The rumor is spreading through a dance. The rumor is spreading through a dance, and you've got this word logistics, so you know you're doing logistic growth. If it doesn't say logistic, you get all your P's on one side, your T's on the other side, all your Y's on one side, all your X's on the other, or whatever. All right, but this is great. It's handed to me ready to go, and oh, it's not ready to go. I can't have anything stuck to the P, so I'm going to have to factor out the 1 over 2,000. The P has already been factored out. Then I say 3 times 2,000, and that would have to be 6,000 minus P. You could redistribute to check it. So now that you have it in KP times L minus P, you know your limiting factor is 6,000. And this number represents the number of people at the dance. Apparently there's about 6,000 people at the dance because that's how many people can hear the rumor. And the rumor's just spreading within the dance. Okay, number 2, it's not ready to go, so I'm going to factor out 0.02, which is 2 over 100, which is 1 over 50. So I'm taking out 1 over 50 and the P, and then I say 8 times 50, and I get 400 minus P. You can redistribute and check and make sure that you got it right before you go on, because this is so easy. All right, I don't even care what these are yet. The limiting factor of each one of these, without even having to find the equation, I know is 400. So the limit as P approaches, of P of the population as time goes off to infinity will level off at 400. So this is a fish pond, so you're putting fish in a pond. If your initial condition is 50 and your limiting factor is 400, your graph will be increasing, and I will sketch that in just a minute. If your population is 300 and your limiting factor is 400, then your graph is still increasing, and I will sketch a graph of that because your first derivative would be positive. If your initial condition is 500 and the lake can only hold 400, then the graph will be decreasing. And so let's stop and draw a picture of those. Let's see. I don't know if I can get more room on this slide. I think all of that's gonna... Okay, good. All right. So our limiting factor is 400. And if we start, half the limiting factor is 200. And 50 is way down here, so it's got a lot of room to grow. And so this one will have a point of inflection. The second one, B, if we start our population at 300, it's only got a little room to grow. And so it looks like this. And then C, if I put in too many fish, they'll die off and look like this if you put in more. All right, so the three equations would be blue would go with A, and green would go with B, and orange would go with C. All right, which of these graphs, A, B, or C, has an inflection point? Only A, because it's the only one that you have a chance to make your first derivative 0. I'm sorry, your second derivative 0. It's the only one, though, that is under half of your limiting factor. Which are increasing, the ones that are increasing are when you put in less than the limiting factor. So it would be A and B. And decreasing, this would be C. To justify your answers, these are increasing because your first derivative is greater than 0. Decreasing, C is decreasing because your derivative is less than 0. And then your inflection point on A, sorry, hang on, I got sidetracked. And your inflection point on A, you could say because your second derivative, you don't even really have to find it, is equal to 0, and it changes signs there. Okay, now that stands for second derivative. It doesn't look very pretty. And you've got your answer sheet. They weren't as clear as I was on this. Okay, here's the tricky one, like number 3. Okay, let's see if I can move this up, or I might have it over here. All right, 3. Okay, so the rate at which a rumor spreads at a high school is 2,000 students. Through a high school of 2,000 students, notice that your limiting factor can be modeled by this differential equation that is good to go, where P is the number of students who've heard the rumor after 9 a.m. How many students have heard the rumor when it's spreading the fastest? Well, it would be half the limiting factor, or it'd be 1,000 students, and it's because that would be the point of inflection, and your second derivative changes from positive to negative. But in logistics, you could say because it's the limiting factor divided by 2. B, oh no, we've got to solve P for a function of T, which if we don't know the trick, would take us a couple of slides. So let's try the trick. All right, so instead of doing all the integration, I'm back to this. Okay. The limiting factor goes on the top with an e to some coefficient of t, and on the bottom I have e coefficient of t. To get the coefficient of t, I multiply these two things together. I multiply these two things together right here, and I get 6. So this is 6. And then I need this number out in front. All right, that number out in front is going to come from L minus P over your initial population. Our initial population is 5, and L is 2,000. So we have lots of room to grow here. So that's 2,000 minus 50. L minus P would be 1995 over the initial population is 5. All right, so here I have, see if I can remember how to get back to that. Close, second credit. Okay, So 1995 divided by 5, I believe is 399. Okay, so this is 399. And so a lot of people leave it like this. Some people divide by this e to the 6t through everything, but I don't even know if they're going to ask you that actually, but there it is in case you do. It's the only way to get, you got to find the original equation to answer these kind of questions. Use your equation in B to determine how many hours have passed when half the student body has heard the number. Half the student body, that would mean my population would be 1,000. So I would go to my calculator and I would put in my differential equation, or sorry, it's not a differential equation, it's the equation, 2,000 e to the 6t, I'll just use x, divided by, remember to put divided by in this time, 399 plus e to the 6t. Okay. And we want to see it hit 1,000. Half of the people in high school have heard it. All right, it probably won't take very long, a certain number of hours. So I'm going to check my window, and I want my Y max to go to 2,000 to my limiting factor. So we'll see logistic growth here, and we can see it hits 1,000. You would go to second calc intersect on yours. See if I can lock it on. There, it's just locked on. And you can see up at the top in blue, you have 0.998. So I had almost an hour. So how many hours have passed when half the population has heard the rumor? It would be when T is 0.998 hours. So it took about an hour for the rumor to spread to half the people. How many students had heard the rumor after 2 hours? So I go to this, and I could go to table. So close and quit. Okay, and I could go to table, and I would fill in 2, but right now I can look at 2, and I can see it right there at 1,995.1089, but you wouldn't give a decimal of a person here. They'd probably ask you to estimate it. So this would be 1,995 people. So after 2 hours, almost everybody knows what's going on because the limiting factor was 2,000. Okay, so number 4, here's our slope field, and we're given this in not the form we want. So I'm going to go over here and make this Kp times L minus P. I got to get that coefficient and that P out. And then you're dividing by 3, and so that gives you 1 minus P. Again, always double check and make sure you have it factored out correctly. In other words, you're dividing, but all of this, you're dividing a 3 out. So, doing it like I did up here, I would say 0.03 times 2,000. I don't even think that even came up on this one. But on earlier ones, you saw me do that. So now double check and make sure you got it right, that you factored it out correctly. All right, so, sketch 3 solution curves. All right, notice they already have 1 here for us as our limiting factor, and 3 different solution curves following the slope field. Sketch 3 solution curves showing different types of behavior. So I could start low and follow this slope field toward 1. I could start up past half the limiting factor, or I could start above it and they would decay or decrease. Describe the meaning of the shape of the solution curves for the population. Okay, so some things that I could say is they're going to be increasing as long as the initial population is less than 1. It's going to decrease as long as the initial population is greater than 1. So I'm using these words to describe it. What happens in the long run? The limiting factor or the carrying capacity is 1. or the limit as t approaches infinity. Are there any inflection points? There would be, yes, especially or only if your p of 0, if your initial population, whatever this is less than half the limiting factor, so is less than 1/2, which would be right here. And so if we started way down here. All right, so where, and that would be what I just said, where your initial population is equal to 1/2, you would have I guess I should have said equal, that's where your inflection point would be, is right here. All right, and what do they mean for the population? So not they, there's only one, but that means that's when your population is growing the fastest. Okay, and then I think we're on our last problem. All right, a certain park is known to be capable of supporting 100 grizzly bears. So I have dp dt. I've got to get this 0.001p, which is 1/1,000, out of there. And if I divide 1/1,000 out of 0.1, which is 1/10, if I multiply those together, I get 100 minus p. Again, you could redistribute and verify 100/1,000 is 0.1, and you kind of have to find your own way of factoring there. So you could also say 0.1 divided by what you're factoring out, 1/1,000, which is why I say multiply them, which would move your decimal, but I'm sure you're good at factoring. You can figure it out, remultiply, distribute it until you know you've got it right. So now I'm going to do A. All right, I've got to find a function for P. I don't want to do that long integration, so I'm going to say P of T. I don't want to have to separate my variables and everything. I don't know what's happening. P of T. That's weird. It wouldn't write right here. All right, so A, P of T, my limiting factor is 100. That goes on the top with an e to some t. All right, to find that, you multiply these two things together, and you get 100, 1/1,000 times 100. And so you get 1/10 or 0.1. And then I've got to say L minus P over P for this number right here. My limiting factor was 100 minus my initial population, which did they give me? Oh, up here. 10 bears are at the park. And so right now there's 10 bears. So at this moment I have 100 minus 10/10. And so that gives me 9. And so you could have this equation, which is on your answer sheet. All right, you use your solution curve to find the number of bears, so I'll let you finish off. You type this in, your calculator carefully with parentheses on the bottom, and fill in 3 for t, and you should get the answer on the answer sheet, 13. And then C, use your solution to see how many years it'll take it to reach 50 bears, because right now there's only 10 when we started. And so for the C part, I would put this in Y1, and in Y2 I would put 50 bears, and you would actually see it grow and hit 50 and do calc intersect, and you should get the right number of years.